for teenage science and spirituality. It is the youth wing, the teenager wing of ISKCON Gurugram, and our purpose is to let people know that there is a scientific and a rational basis behind spirituality and behind God. The reason why most of the people are deprived to accept God is because of they do not get very logical arguments, and the atheistic scientific theories that are presented to them, it makes it very difficult, and they find no answers to these questions. So our temple president is amongst us, His Grace Ram Bhadra Prabhuji. Prabhuji was very compassionate for these kids, because the reason why uh, most of kids, like I was telling you, people like yourself, like me, they don't get answers, and that is why they lose their faith in spirituality. So Prabhuji, we started this program in 2020 in lockdown, and this is here right now. So Ram Bhadraji is the temple president of ISKCON Gurugram, and he he is a monk, and he is a spiritual coach and a corporate trainer as well. He has been giving sessions on spirituality and the practical applicability of Bhagavad Gita and other such scriptures in their daily lives. What is the relevance? He is training people of all ages, and he has opened many such programs, especially in this times of COVID, due to kind nature. He distributed 2.5 lakh meals in Gurugram alone, home delivery, and for that he was felicitated by World Book of Records as a certificate of commitment. So I would just request Prabhuji to please introduce Michael Behe.
Hare Krishna. Am I audible? No? Am I audible? Hare Krishna.
Yes.
So very warm welcome to Dr. Michael J. Behe. Thank you for accepting our request for coming in our program. So we really like to have your association with the kids here. So thank you very much for accepting our request. We're really happy to see here. Wonderful. Yes. So Doctor is a revolutionary biologist and author and a professor of biological science at the University of Behe, Pennsylvania, United States of America. And then we see the Srila Prabhupada, the founder Acharya of ISKCON. He was established to God consciousness. He wanted that the ISKCON, the God consciousness should be spread to a scientific way of. So he wanted to establish the God consciousness through scientific basis and argument. So with this purpose, Srila Prabhupada opened a Bhakti Vedanta Institutes. And then many of the Srila Prabhupada disciples go through PhDs and various scientific disciplines to expose the atheistic scientific theories and prove the existence of God. So one such a spiritual scientist was Dr. T.D. Singh, Bhakti Swarup Damodar Maharaj, who wrote the many books in a collaboration with various scientists. He also wrote the books God, Intelligent Design, and Fine Tuning in collaboration with Professor Michael Behe. So Michael Behe is the world's famous prominent theory of the intelligent design, senior fellow at the Discovery Institute Centers for the Science and Culture. Their aim is to prove the scientific audience that physically force and the present scientific theories are incomplete to explain in many things in the universe. And therefore, they propose the existence of an intelligent designer in the nature, which is God. So he has written the 3 books, Darwin's Black Box, Darwin Devolves, and Edge of Evolution. So his books, Darwin's Black Box, was nominated by the National Review and the World Magazine in the 100 most important books of the 20th century. He presented and debated his work at the various international universities all over the world. So no scientist till date has been able to refute the arguments he has given to prove the existence of an intelligent design in nature. His recent video series, Secret of the Cell, has been critically acclaimed, is available on the free on Discovery Science YouTube channel. So thank you so much. I'm not taking so much time. So thank you for joining us and accepting our invitations. Thank you very much. Thank you, Michael.
Thank you. Thanks very much for that very nice introduction. I'm delighted to be with everybody. It's an honor for me to speak with so many people. So let me just share my screen with you to start off. Let's see. Okay, here we are. Excuse me. Okay. Now, excuse me. Let's see if I can do this correctly. Okay, here we go. Just one more thing. Okay. Okay, so I titled my talk Darwin versus the Borg, the nanotechnology of life. I'll speak for about 40 minutes or so, and then we can have questions. But many of you may have seen the TV show Star Trek, and in some of the later episodes, the enemy is the Borg, which is a half human and half machine living being. And it is run by nanotechnology, which are machines that are so small that you really can't see them with your eye. And what I'll show you today, and part of what I'll show you today, is that you are like the Borg, because much of your biology, much of the work that has to be done in your cells is done by nanotechnology, by really machines made out of molecules. But before we get to that, I'm going to review a little bit of history of the debate about where we came from and how we got to be here. So before Darwin, almost everybody in the whole world agreed that we humans and life in general were the result of God's work, of purposeful, intelligent design. For example, here's a man named Galen, and he lived 1800 years or so ago, and he was a Greek physician, and he was the most prominent scientist of his time. And he wrote that the human body is the result of a supremely intelligent and powerful divine craftsman. That is the result of intelligent design. And he said this not just because he was religious, although he was, but because he was a physician and he dissected organisms like plants, and he studied the human body, and he was amazed by all the many amazing systems that he saw. And this same view of life continued from Galen's time on. For example, here's a man named William Paley. William Paley lived around the year 1800, and he was an English clergyman and a philosopher too, and an amateur biologist. And he made a famous analogy about a watch. He wrote that, excuse me, if we found a watch in a field just at our feet, well, if we found a rock at our feet, we wouldn't think anything of finding a rock. But if we found a watch at our feet, then when we came to inspect the watch, we would perceive that its parts are framed and put together for a purpose. That because the parts are so formed and adjusted as to produce motion, and and from that we can tell the time of the day. So he concluded that the inference, we think, is inevitable, that the watch must have had a maker. And he concluded that because all of the parts were arranged for a purpose and that we could see that purpose. So for the entire history of the world, up until at least the year 1800, pretty much everybody, religious or not, educated or not, rich or poor, knew that life had to have had an intelligent designer. But in the 19th century, this man, Charles Darwin, wrote a book that changed a lot of people's thinking on the matter. Darwin lived in the 19th century, and when he was a young man, around 23, not much older than many of you folks listening now, he went on a voyage. He went on a ship called the HMS Beagle, shown over here. Let me stop a second and get a get a pointer. Here we go. Maybe this will be easier to see. Here we go. So he sailed on a ship called the HMS Beagle, which was an exploring vessel. The English sent out ships to see parts of the world they didn't know anything about. And so he went from England all the way down to South America and at several points, and then over around to some islands, and then over to Australia and up close to India and Southern Africa and back again. And from his voyages, he was able to see, he discovered animals that lived in other parts of the world, not in Europe, that were similar to ones that were in Europe, but different. For example, in the Galapagos Islands, which are just some small islands about 500 miles west of Ecuador, west of South America, he saw a number of different species of finches. And he was puzzled because there weren't that many finch species on the continent of South America. And he wondered why on these little islands there should be so many species of finches. And later on, after he got back to England and thought about it for a while, he came up with his idea of evolution by natural selection. And the important points of his theory are that individuals of any species can vary. You know, some members of a species, say rabbits or dogs or cows or plants, members of a species can vary. Some are bigger, some are smaller, some are faster, some are brighter in color. And Darwin thought that some of those accidental variations might favor survival. Maybe a member of a species that was a little bit faster would survive better than others. And those that survived could leave more offspring. They could have more children. And if that variation, and if that trait, the ability to go faster or slow, or faster or be larger or whatever, if that trait was inherited, then over the generations, more and more members of the species would have it because the ones who had it left more offspring. So, this was his idea of evolution by natural selection. Over time, the whole species would change, and then maybe another variation would come along, and the whole process would repeat. And that over time, perhaps the species would change quite a bit. So that was a good idea. It could explain perhaps the variation in the finch species in the Galapagos Islands. But Darwin, extrapolated his idea and tried to explain all of life with it. Well, when we try to judge Darwin's theory, we have to remember that it has multiple parts. That is, there are different ideas all packaged together, and the one package is called Darwin's theory. But some parts of his theory might be right, and others might be wrong. And for our discussion today, the three most important parts of Darwin's theory are these. First is the idea of common descent. That is, that organisms that are alive today are descended by birth and death from organisms that lived in the distant past. And as I wrote, that's interesting, but it's actually really a trivial statement, at least in trying to explain how life got here, because common descent just says that there were ancestors in the past, but it doesn't explain where they came from or how they came to have the traits that they did. And it says that they gave rise to organisms in our present time, but it doesn't say by itself how the organisms, why the organisms in modern days differ from the ones in the past. So as I write, the idea of common descent is interesting, but it's trivial. It doesn't explain how things got here, or how they change. The second part of Darwin's theory is the idea of natural selection. That is, that some organisms that have a random trait will survive better. And again, I think that's interesting, but ultimately it too is trivial, because if you're going to say that there are organisms that are better or that are more fitted for their environment, well, of course, they're going to survive better. You know, who's going to deny that an organism that is more fit will do better in the world than one that isn't? The third and most important part of Darwin's theory is the idea of random changes, or random variation, random mutation. The critical claim of Darwin's theory is that random changes without any perspective of how they're going to help the species, random mutations can be the supply for natural selection to work on and to make all of the species, the wonders of life that we see today. Okay, so that's the introduction, a little bit of history. And now I want to shift gears just a little bit just to make another point. Okay, this fellow here is a man named G.K. Chesterton, and he was an English writer who wrote around the turn of the 20th century, about 100 or so years ago. And he wrote a book called Orthodoxy. And one of the things he wrote was that nursery tales for children, nursery tales say that apples were golden only to refresh the forgotten moment when we found that they were green. They make rivers run with wine, only to make us remember for one wild moment that they run with water. And the point that he's trying to make here is that many things in our everyday world are astonishing. They're really crazy, but because we see them all the time, we take them for granted. And that nursery tales or fairy tales or tales for children try to put these fantastic facts into a different context, just to shock us into recognizing how amazing they are. So what I want to do is to put kind of the facts of biology into a different context, to try to shock you, try to shock everybody out of taking them for granted. And the fairy tale, the tale for children that I want to allude to, is Star Trek. Now, I'm a big Star Trek fan. I hope a lot of you have been able to see it, but Star Trek, of course, is a science fiction TV show that was about exploring space and all the space aliens that the folks would meet out there. And here's the crew. This is Captain Picard. And one of the enemies of our heroes on the spaceship are called the Borg. And if you look it up on the internet, the Borg are, if you look up nanotechnology is a word used to describe devices so small that the naked eye cannot see them. The Borg Collective is infamous for their use of nanotechnology to advance their goals, assimilating new members and technologies with it. Okay, so here's some pictures from the internet that I got that are from Star Trek, and this is actually the captain of the good guys, the captain of the Starship Enterprise. His name is Picard, and he is being taken over by the Borg, and they put nanotechnology into his bloodstream. These little things are red blood cells. And here are these evil looking machines with little metallic parts and so on that are kind of refashioning him. Now, again, as I said in the beginning, what I want to emphasize is that in a sense, you are the Borg. You have been taken over. You have been assimilated because all of us, modern biology has discovered that all of us are run by really sophisticated molecular machines, nanotechnology that nobody ever dreamed of before, 50 years or so ago. As a matter of fact, the machines are much more sophisticated than this crude little drawing that somebody in Hollywood came up with. For example, here's the cover of a scientific journal called Cell from about 20 years ago. And it's a special issue on molecular machines. Molecular machines. You see down in the corner here, this looks like something like William Paley's watch. And if you turn the cover of the journal and look at the table of contents, you see articles such as the cell as a collection of protein machines, polymerases and the ribolosome, machines within machines, mechanical devices of the spliceosome, motors, clocks, springs, and things. So I want to point out that it's not just me or intelligent design proponents who point to the complexity of life as an indicator of design. It is all of biology that says that we are run by very, very sophisticated molecular machines. Now, I could talk about these for a while, but since there are a number of videos on the internet which illustrate some of these things, for the next few minutes, I'm going to show everybody some videos of molecular machines in action. And the first thing I want to say is that here's a little cartoon drawing of something called a protein. Now, it turns out that although people think of proteins as something you eat, one of the major food groups, scientists have discovered that the machines in our body are made of things called proteins. And proteins are polymers that are made up by hooking together things called amino acids. In a sense, it's like a written language, like letters that are put together to form words. In the English language, there are 26 letters of the alphabet, but with just those 26 letters, one can put them together to spell out anything, to write books, to write encyclopedias, whatever one wishes. In the same way, in our bodies, there are 20 different kinds of amino acids, and they can be put together in different sequences to make machinery, all sorts of different kinds of machinery. So when they are put together, they have special properties. Because of the forces between them, they can fold up. Instead of just being a long chain, they can fold up into discrete structures. For example, here's a chain of amino acids that folds up into this helix and then can fold further into a definite shape, and then it can associate with other proteins to form a machine, a protein machine. This here is a little cartoon drawing of hemoglobin, the molecule in your body that carries oxygen from your, as you breathe it into your lungs, and it has to be distributed to your tissues. Okay, let's look at a couple of levels of how proteins work. Here's the next slide. Here's a single protein chain. And I just want to show you how complex it is. It has to fold up into a definite shape. Let me kind of zip ahead a little bit here. Okay, here's the, okay, here is the protein chain. It doesn't have all the features shown here, but this is a computer simulation of how the chain, one single little chain, has to fold itself. It has to form by regions that attract other regions, and other places of the protein chain that want to fold and get away from water. Others like to be in contact with water. And eventually it starts to come into a particular shape. I'm going to zip ahead here. This is a little helix that's a definite part of the protein. These little things here are strands of other parts. And so at the end, here, let me go to the end, it folds into a definite shape. It's kind of like having a long chain, and when it folds, it forms a hammer. A hammer. So it can fold itself into a hammer, which can be used as a tool to do a particular job. And if you had another chain, it would fold differently, and it might fold into a saw, which helps do a particular job. Now, just like a hammer depends on its shape to do its work, and a saw depends on its different shape to do a different job, all machines depend on their shapes to do their particular jobs. And it's the same thing with proteins. They have to assume particular shapes in order to do their work. Now, proteins oftentimes don't work just by themselves. They have to get together, just like a club or an organization of people. They have to get together to do the work peculiar to them. And that's shown on the next slide. Let me see if I can get this. Okay, here's an example of proteins that have to associate. These triangular type things are called triskelions, and they all come together automatically by attracting each other with positive and negative charges and other things. And they form this large ball. And this is like a container, a vessel. This can be used by the cell to package materials. And the materials are then transported from one part of the cell to the other inside this container. It's crazy, you know, it's crazy. Okay, so this is made of copies of just one kind of protein, but there are other I'm sorry. Oh, I'm sorry. I hit the wrong button. Here's another machine called an ATPase, and I'm going to let this play. This has some audio narration, so let's listen to it for a little bit. This is a really sophisticated machine that's responsible for making much of the energy that is made in your body and mine. Here we go.
Life requires energy. The universal biological fuel is a molecule called ATP, or adenosine triphosphate. ATP stores chemical energy in the form of a high-energy phosphate bond. As the name suggests, it consists of an adenosine ring with a chain of 3 phosphate groups attached. The last of these phosphates can be split off to release the energy within the bond, resulting in adenosine diphosphate and free inorganic phosphate. This energy is needed to keep cells alive and is used from processes from muscle contraction to producing the thoughts your brain is having right now. The hydrolysis of ATP can be reversed by the addition of inorganic phosphate to ADP. However, this of course requires energy and is performed by a molecular power generator called ATP synthase. Here we see an atomic model of F1-FO ATP synthase sitting in a membrane. This molecular motor is found in the mitochondria of eukaryotic cells and is responsible for making most of the ATP. Mitochondria, the powerhouses of the cells, turn over around 60 kilograms of ATP every day in an adult person. A long chain of biochemical processes convert the energy stored in food into a proton gradient across the inner mitochondrial membrane. These protons drive a rotation of the turbine within ATP synthase, resulting in the synthesis of ATP. Like all generators, ATP synthase consists of 2 separate motors coupled together. Within the membrane, we have the FO motor, named after the binding of antibiotic oligomycin, and at the top we have the F1 motor from factor 1. The FO motor is a proton-powered motor. It is thought that protons flow through a channel open to just the intermembrane space, where they bind to a ring of protein subunits, rotate 360 degrees, and exit through another channel exposed only to the matrix. The net flow of protons driven by the proton motor force provides the energy for the generation of rotation. The torque generated in the FO motor is transferred to the F1 motor by a central stalk or shaft. The F1 motor is responsible for generating the ATP by addition of phosphate to ADP. The top of the central stalk acts similarly to a camshaft, so that as it rotates within the F1 motor, it causes conformational changes of the catalytic subunits. The catalytic unit is made of a dimer of subunits, and there are 3 of these arranged in a ring. Catalysis occurs at the interface between the dimers. If we concentrate on one dimer, we can observe 3 distinct states. First, ADP and phosphate bind to the catalytic site. The central shaft then rotates 120 degrees to rearrange the molecules. Next, the enzyme undergoes a further 120-degree rotation, and the ADP and phosphate are fused together to create ATP. The enzyme then rotates again to return to the starting position, where ADP is released and ADP and phosphate can be bound for the next cycle of catalysis. One key aspect of this relationship is that catalytic subunits must remain stationary with respect to a rotating central shaft. This task is performed by a scaffold on the outside of the complex, referred to as the peripheral stalk. Recent work has shown that what was once thought of as a rigid scaffold is actually dynamic and is able to accommodate the changes necessary for most efficient function.
Okay, I think we've seen enough of that. If you're not familiar with it, it might look a little hazy and you might not know what a proton motive force is and other details. But I want you to see is that this is a machine. This is a real sophisticated molecular machine, and it's necessary for you to be alive. It's necessary for all organisms to be alive. It's found from bacteria up to people. And this is the kind of thing that theories of how we got here, theories of life, have to explain. It's not just tiny little changes in finches that were already on islands. It's the existence of astoundingly sophisticated machinery and integrated biology. I'm going to skip ahead now. Let me try to skip ahead if I can. Oh, here's another view of that same molecule, ATPase. And you can see it rotating, and this rotating down here drives the motor that's on the top of the machine, which crushes together two different molecules and makes them chemically react. And that's the basis of our energy, the basis of the power that we have. Okay, I'm going to skip ahead a couple of slides to this one. This is going to show a number of machines, and not just in a cell, but in one cell, and how it goes out and is necessary for an organism to live. It shows how cells in the body react to an infection, to a threat from an invading bacterium. Let's take a look at this.
This is the story of a white blood cell that finds an infection and goes through the wall of an artery in order to stop that infection. What you see now is called a lipid raft. It's made up of special phospholipids that pack tightly together and hold together the membrane proteins that are specifically linked to that lipid raft. These lipid rafts move around in the phospholipid bilayer and coordinate activity. Now we are zooming down one of the microvilli inside of one of those microvilli protrusions. And what we see now is the polymerization of actin from the actin monomers, and actin forms the cytoskeletal network. This is gelsolin. It cuts off a part of the actin filament. Now we see microtubulin assembling from tubulin monomers, and this is called catastrophe when the microtubules move back. This is kinesin walking along the microtubule and pulling behind it a vesicle. And along this picture you can see a lot of microtubules, all with vesicles being pulled by various motor proteins. And in the center is the centrosome with its centrioles. This is the cell surface, the nucleus surface with the nuclear pores, and mRNA is coming out of the nuclear pores and now is assembling with a spliceosome that allows the mRNA to be processed before the ribosome, which is shown there, begins to read the mRNA and produce a protein. This is another ribosome assembling onto the surface of the endoplasmic reticulum, or the Golgi body, and in this case it's producing a protein that will be secreted. It's contained inside of a vesicle, inside of that membrane coat, and pulled to the outside of the cell by such a motor such as kinesin, which is shown here. And these are vesicles that are being dragged from the Golgi body, which is shown right here, to the outside of the cell, and we're going to watch them being secreted into the space between the membrane and the extracellular matrix, which is above. These proteins are secreted, but they don't leave the membrane because they're bound to the membrane. And these are the proteins, the ICAM, that can reach up and bind tightly to the receptor molecules on a cell that is signaling a problem somewhere behind the cell. Once ICAM binds, it allows the white blood cell to go through a conformational change where the actin matrix dissolves, and it allows it to slither into the region where it needs to eat up the bacteria or the infection. This
Okay. Again, you might not have followed everything, but the point I want to get across is that biology is astounding. It's astounding. Cells aren't just little squishy pieces of jello. They're sophisticated beyond our imagining. And that one cell and all cells in our body are integrated. And just to stop an infection, as that video showed, all of these coordinated machines and systems have to act together in order to fight it. So that's something you often don't hear about in biology, but this is the result of modern science. This is what modern science shows us. And here's a cartoon slide, how most people think of evolution. And here's a little funny, here's the wife complaining to the to the husband fish, don't walk away when I'm talking to you. And that's how that's how legs got started. And here's a little drawing of a dinosaur with feathers. That's fun to think about too. But that's not the problem. This is the problem that we have to solve. The information, the astounding amount of information that is packed into biology and the DNA that runs each of us, and the molecular machinery, this little cartoon here, the molecular machinery that allows our cells to run. So when somebody tells you that science has it all figured out and talks to you about some fossils, ask them about molecular machines instead. Okay, so we are made by these astounding machines. Why should we think that life was purposely designed? And this is, I should emphasize, this is not just a negative case that Darwin's theory can't explain what we just saw. This is a positive case for design, that the evidence for design is overwhelming. And we conclude design every time we see an eagle fly or every time we see a fish jump out of water. Why do we do that? Well, we have to ask ourselves, what is intelligent design? And if you look in a dictionary, design is defined as the purposeful or inventive arrangement of parts or details. And we can shorten that just to say design is the purposeful arrangement of parts. And that means that when we see some things that are put together and we can see that they have a purpose, we will conclude that there is design. And so that's just some words. We infer design whatever parts appear to have been arranged for a purpose. Let's look at an example of that on the next slide. Okay, here's a cartoon that I like. And this is a cartoon of some explorers, and the lead explorer has been caught in a trap and strung up and skewered. And this fellow turns to this guy and says, "That's why I never walk in front." Good thinking. But what I want to point out is that everybody looking or attending this talk today, you look at this cartoon and you immediately understand that this was designed. This is not an accident. His death was intended. Now, how do you know it was designed? You know it was designed because you see a number of parts that have been arranged for a purpose. You see the purposeful arrangement of parts. And let me emphasize that it's not a religious conclusion that this was designed. That would be kind of weird. This is not a religious conclusion. This is a completely empirical conclusion. We conclude design from looking at the physical components of a system and seeing that they're arranged for a purpose. So the conclusion of intelligent design is not a religious conclusion or a philosophical conclusion. It's a scientific conclusion. It's based on the physical evidence plus ordinary principles of logic. And it turns out that perceiving a purposeful arrangement of parts is the way, the only way that we recognize the work of a mind. We have minds, we can think, we have purposes. And when we see something that has been arranged for a purpose, then we infer that another mind has acted. This is a famous statue called The Thinker by a French sculptor named Auguste Rodin. And we can see that this was purposely arranged. A sculptor, arranged the pieces of the material into a shape for a purpose. So we can recognize the work of a mind in the purposeful arrangement of parts. Now, in order to avoid confusion, you have to keep a couple other points in mind. And the first point is that the strength of the design inference is quantitative. That is, that the more parts we have and the more closely they are arranged for a purpose, the more and more certain we can be that design has occurred. And here's some examples of those. If you walked by these mountains in Idaho in the United States, you might think they're pretty, but you wouldn't think that they were designed specifically as they are beyond the laws of nature. You would just think they were pretty mountains. If you walked by this structure called the Old Man of the Mountain in another state in the United States called New Hampshire, you'd look at this and you'd say, oh, this kind of looks like a face. This is a forehead and a nose, and maybe this is a mouth and a chin. You might wonder, maybe some prehistoric people were going to put that together. But then you look at it and you say, man, no, it's just a strange arrangement of rocks. But then suppose you walk by these mountains in the United States called Mount Rushmore. If you walk by here, you would immediately know that these were purposely designed by an intelligent agent. These are four figures of former presidents of the United States. And you would know they were designed because you'd see the shapes of the rocks have been fitted to portray these images. They were fitted for a purpose. So you see the purposeful arrangement of parts. So again, the point is we perceive design from physical characteristics of a system when we perceive its purpose. And since it's perceived from physical parts, we can have more parts or fewer parts. And so our certainty of the conclusion of design is quantitative. Another point that you need to keep in mind is that design can be found at multiple independent levels. You can have multiple levels of design. For example, here's a store that sells building supplies. And here you can see bricks and pieces of lumber, and you can see that they were shaped, and they're shaped for purposes to be parts of, to be building supplies. And you can see some arrangements of these materials, but this arrangement can be used in a number of different buildings. We can tell that this was purposely designed, but all of these materials, all of these design materials were used to independently come up with this house. So we can easily determine that this was designed and this too, but we couldn't tell that necessarily this was going to be used in this or that these were going to be used in this. So multiple levels of design. Okay, so about more than 25 years ago, I wrote a book called Darwin's Black Box, and I pointed out many of the things that I talked about in this talk so far today. But I also pointed out a big problem for Darwin's theory that the scientific discoveries we've seen pose to his mechanism of random mutation and natural selection. In The Origin of Species, Darwin wrote that if it could be demonstrated that any complex organ existed, which could not possibly have been formed by numerous successive slight modifications, my theory would absolutely break down, adding, but I can find out no such case. So numerous successive slight modifications. Darwin always insisted that his theory of evolution had to work gradually. Organisms had to improve slowly in tiny steps over long periods of time. And he always insisted that because he knew that if life improved suddenly in large leaps, then it would look strongly as if this was not a chance process, that it was purposely done. Well, okay, let's take Darwin at his word and ask ourselves, what could not be built by numerous successive slight modifications in the gradual way that Darwin envisioned? And I wrote back 25 years ago that a system which resisted Darwin's theory is one which I termed irreducibly complex, or had a property of irreducible complexity. And that's kind of a fancy phrase. It just means that a system needs all of its components to work. And if you take one away, it doesn't work anymore. And a good example of the idea of irreducible complexity from our everyday life is just a mousetrap. For example, a mousetrap that a person can buy in a hardware store in the United States has a number of different components. It's got a wooden platform to which everything else is attached. It's got a spring. It's got this hammer, the holding bar, and so on. It turns out that all of these parts are needed for the trap to work. If the spring was not there, if the platform were not there for other things to be attached to, if any of these components weren't there, it's not like it would work half as well as it used to. It would be broken. It wouldn't work at all. Now, the relevance to Darwin's theory is that with irreducibly complex systems, you have to have the whole thing together before it works. There is no gradual pathway that could be taken randomly that would arrive at this thing, because it only works when this system is pretty much complete. And it turns out that science has discovered the machinery of the cell is irreducibly complex. In fact, almost all machinery is irreducibly complex. If a simple mousetrap such as this is a problem for gradual evolution, how much more the sophisticated machinery of the cell is too. And in my book, I pointed out another machine of the cell called the bacterial flagellum. And this is quite literally an outboard motor that bacteria use to swim. This is a motor, literally a motor down here, and it spins in a rotary motion. And as it turns this drive shaft, which turns this universal joint, which turns this long filament, which acts as the propeller, and it spins around, and it pushes against the water and pushes the bacterium forward. And this is attached again through these universal joint to a drive shaft, to the motor, and it has all of these different parts. It's more sophisticated than the ATPase that we talked about just a few slides ago. And like a mousetrap, it's irreducibly complex. If you didn't have the drive shaft, if you didn't have the attachment region here, if you didn't have the propeller, it wouldn't work. It's not that it would work inefficiently, it wouldn't work at all. So Darwin's mechanism has a very, very difficult time with these things. Let me just jump ahead now. Make a point that irreducible complexity, like we just talked about, has a double use. It makes 2 points. Number one, it's a big problem for Darwin's mechanism because you can't build irreducibly complex systems step by gradual step as he envisioned. Additionally, in an irreducibly complex system, all of the parts are arranged for a purpose, the purpose of the machine, just like the mousetrap. So it's both a problem for Darwin and a strong pointer to purposeful design. Okay, I'm going to skip ahead now. Let me just say that, these were great slides. I wish I had more time, but I really don't. Look at this. Oh, here's another molecular machine. This is a virus, bacteriophage T4. It's like a space lander that lands on cells and injects DNA into them. Holy moly. And here's a nice quote I like to show people from a man named Franklin Harold, who was an eminent biologist. He died about 10 years or so ago. And he wrote a book called The Way of the Cell, which was published by Oxford University Press, a very prestigious academic publisher. And towards the end of the book, he touched on intelligent design. And he didn't like intelligent design. And he had this to say about it. He said that we should reject, as a matter of principle, the substitution of intelligent design for the dialogue of chance and necessity. And he referenced my book, Darwin's Black Box. But we must concede that there are presently no detailed Darwinian accounts of the evolution of any biochemical system, only a variety of wishful speculations. So he said in 2001, and 20 years later, the situation is still the same, that there are no Darwinian explanations for these systems, only wishful speculations. And what do we mean by wishful speculations? Well, just so stories. There was an English writer called Rudyard Kipling, and he wrote some children's stories about how the rhinoceros got its horn and how the elephant got its trunk, and how the bacterium got its flagellum, stories like that. But if Darwin's theory can only come up with children's stories about how life formed, then it's probably not the best explanation. And remember, Franklin Harold said we should reject intelligent design as a matter of principle. What principle is that? Why should we reject intelligent design if it's so utterly obvious in the machinery that we've just looked at? Well, Franklin Harold didn't say, he didn't write in his book. He just wrote that and then went on to other matters. But I have a good idea what the principle is that he had in mind. And it's shown here on this next slide. This is the principle. This is a Ghostbusters sign. I don't know if it's a movie from a long time ago, 20 years or so ago. Maybe some of you have heard about it or seen it. And essentially, the principle that Franklin Harold said is that scientists get nervous when things in science start to point beyond nature, and they think that science should stay away from that. But I was always taught that science should follow the evidence wherever it leads. And if the evidence points strongly to design from an intelligence that is much, much more powerful than any of our best minds, then we should follow the evidence where it leads. Okay. Oh, here's another good one. These gears have been discovered in some insect legs. I wish I had time to go into a lot of this stuff. I'm going to skip ahead though, and just say that the conclusion is that intelligent design is rationally compelling. It is not a religious conclusion. It might have very strong religious implications, as I think so myself, but it's based on the evidence, the physical evidence discovered by science, plus just normal ways of reasoning, that a purposeful arrangement of parts is evidence for design. Now, I've been in talking about this for a long time, 25 plus years. And in that time, there have been a few people who have disagreed with my conclusions. And so I have a web page where I have put up responses to criticisms that I've received over the years. So if you want to follow the criticisms and my replies to criticisms and the back and forth, there are a couple of places that you can go to see. One is my website at Lehigh University, another is a Discovery Institute website. And then there's a website that's associated with my latest book called Darwin Devolves. So with that, I'm sorry I went so long, but I can stop sharing my screen now and say I'd be happy to answer any questions if people have time to stick around and ask them.
Yes, sir. We'll have. Am I audible to you?
I'm sorry?
Am I audible? Clearly?
Yes, I can hear you. Yes, just fine.
We'll have the question answer session now.
Okay.
I'll just like to give a brief summary. There were many different points actually which you put up, sir, and those were totally amazing. I was talking with a lot of people in between, and they were really happy. They were saying that, no, this is a different world altogether, and we did not know that such detail existed. And some of them are very happy that now they'll be able to answer their atheistic friends. They'll have something to say. So,
good. Yeah. The important thing to remember is that the more science knows, the more strongly it points beyond nature, that nature can't explain itself. We need something God beyond nature to account for all the things that we find in nature.
Yes, sir. So one point I really liked was that the same thing. You were telling that we are actually not against science. We are scientists, and modern science is also showing us this. So science teaches us to follow the evidence, and wherever it leads, we should go over there. So if science is leading us towards the evidence of design, then we should not reject it, we should accept it. And this thing does not have a religious implication or a religious conclusion. This is coming from empirical evidence on which science is based. So this was really great. And the one thing, irreducible complexity, you have to have the whole thing together before it works. So if a simple cell, a simple bacterial flagellum cannot be broken down into simpler means, because if it is broken down, then it will not work. So that means that even a small bacterial flagellum cannot come by chance, cannot come on its own. So what to speak of the beautiful life around us? And you very well explained it through that example of mountains, the Rushmore Mountain and the Old Man Mountain. So
right.
Yes, I have these questions, so I'll just ask it one by one. Okay, I am asking Swastik. Swastik Verma can unmute and speak. Sir, is it okay if we allow people to unmute and speak?
Yes, please.
Okay. Swastik followed by Parth.
Yeah, I wanted to ask that, does the existence of appendix discredit the claim of irreducible complexity in our body?
Oh, okay. My hearing isn't as good as it used to be. Could you repeat that, please?
Okay, I wanted to ask if the existence of appendix discredit the claim of irreducible complexity claim.
The existence of what?
Appendix.
Appendix in the body.
Appendix. Okay, that's an excellent question. The appendix is an organ, of course, in our bodies that is dispensable in a sense. It does do useful work, as scientists have shown over the past few decades. Its function used to not be known, but apparently it has a function in the immune system, and it helps defend us from bacterial infection. Nonetheless, you can have an appendix removed and you still live. So the question, I think, is does that challenge the idea of irreducible complexity?
Right.
And the answer is no, not if you and not if you're talking about irreducible complexity the way that I defined it. And in my book, Darwin's Black Box, I'm careful to say that irreducible complexity is a single system, say like a mousetrap, where you can take away one piece and the system is broken. It stops working entirely. The problem is if you take away the appendix, it doesn't stop working entirely. As a matter of fact, it can still work for a little while. Irreducible complexity does not mean that if you take something out of a living organism, it dies. That's different. You can take a heart out of an organism, or you can take a heart out of an organism and the organism will still live for a few seconds. The cells inside the organism will still perform many of their processes. That's not the same thing as the irreducible complexity I was discussing. With a mousetrap, if you take away the spring, it can't work. It has no ability to work. What's more, with the appendix is not just one system like a mousetrap. An appendix is composed of many cells. Each of those cells has ATPase in it. It has intracellular transport systems. It has kinesin. It's got all of the systems that were shown in some of these videos. So it's a multiple component system. So you have to be pretty careful when you talk about irreducible complexity. And when I do so in Darwin's Black Box, I shifted the focus from organisms, from living complete organisms, down past organs, down past things like the eye, down to the very foundation of life, the molecular foundation of life, because that's the basement of life. It's like the nuts and bolts of machinery. You have to look at the molecular level of life to see what is irreducibly complex and what isn't, because even simple cells, quote unquote, are made of many different sophisticated molecular machines. Some of those machines you can take away and the cell still lives, but if you take parts out of the machines, the machinery breaks. Let me give you another analogy here. If I had, here's my computer mouse, okay, and I can use it to move this cursor around. If I took the mouse and took the battery out of it or did something else, the mouse might break. But my computer could still work. I can use this touchpad on the surface. The computer works just fine. But if I took the battery out of here, the mouse would be broken. So the mouse might be irreducibly complex if it were a single system, but it can be a component in a complex system that has a number of different systems working to do something else, a higher level of design. And that might be able to continue if one of the subsystems is removed. But if you take a component out of the subsystem, that might stop working. And then this is irreducibly complex, but the higher computer is not. And that's because it's a collection of irreducibly complex systems. It's not just one. I hope that helps a little bit anyway.
Thank you.
Yes, sir. Thank you very much. Next, I would like to ask Parth Mahajan to speak.
Hi, Doctor. Thank you very much for that talk. I personally am a creationary evolutionist because I've read up a little bit on this. And my question to you is, so do you believe then that there has been no change in cerebral capacity? Have we always been dexterous, meaning have we always used had limbs and fingers and toes, and have we always been a bipedal species? Because there is evidence to say that we weren't always like this. So are you saying that we've always been this way from the advent of the human species in the planet, or are you saying that there is a mixture of both creation and evolution?
Okay, that's a great question. Thanks very much. Okay, so the question is, okay, we say that, Darwin's mechanism can't explain what we've got here, what we can, our fingers and toes, our ability to think, and so on. So does that mean that we were created intact all at once in a puff of smoke or some such thing? And the answer is no, not necessarily. Intelligent design, the idea of intelligent design doesn't say or doesn't get into the question of how the design was made. It just says that we can see from the purposeful arrangement of the parts that design was necessary in putting things together. The question, the important question, as I pointed out in one of my previous slides, is not common descent, and it's not natural selection. The important point was random processes. Did all of the sophisticated biological systems we see, are they the product of just random changes plus natural selection? Darwin's claim to fame, Darwin's main importance is not that he proposed common descent or that animals living today are descended from animals or other things living in the past. Before Darwin, there were a number of other people who proposed that life gave rise to different kinds of life. But in those cases, it was always a teleological process. That is, it had a purpose. It was directed or by some natural principle or by a supernatural principle. It was not random. Darwin's importance was to say that no, there is nothing outside of life that is needed to develop it. He famously said that he saw no more design in life or direction in life than direction in which way the wind will blow. So he's just saying random changes and natural selection are sufficient to explain life. And I tried to illustrate today why I think that's incorrect. This does not say anything about the question of common descent. If an intelligent being, if a very intelligent, supremely intelligent being wanted to direct the unfolding of life over time, wanted to guide how life developed and did so, either by somehow programming the unfolding of life into life's history or actively guiding it somehow, then who am I to say, he couldn't do that? But the important point is that if that were the case, if evolution were guided, if the unfolding of life were purposely channeled, then that is intelligent design. That is not Darwinian evolution. The important thing is that Darwin said there is no purpose, there is no direction, there is no intelligence in the unfolding of life. Intelligent design says we do not know how the life was directed, or how it was the mechanism by which it was brought into being, but we can tell by the structure of those machines, by the arrangement of parts, that it was done purposefully and that there was an intelligence behind life. So I hope that helps a little bit.
Yes, sir, indeed. Thank you. So we have a series of questions at the moment. We have around 10 more questions. So how should we go about it? Do you suggest?
Okay.
I guess if we can quickly ask them and get those answered, because these people were really eager for this session, and I'm not sure when will they get your audience next time. So
Okay,
yes.
next then.
Dr. Anshika Negi, you can quickly ask your question and then we'll move to next.
Hello.
Audible,
Yes.
ma'am.
Okay. Thank you, Dr. B, for such a wonderful session. Actually, I want to ask that the virus part, because virus is designed in a way that it is living inside the body, but it is dead outside. So you are explaining that every molecule, like even the ATP synthase or any molecular like motor, kinesin, dyne, everything is working. If they have a design, they are working. But why such that virus are not working if they are outside? Virus should also work. If they are designed in a way, if they are intelligently designed, then they should also work outside the body. Why are they only working inside a body?
A designer, I think, could make machinery or could make things that is intended to do something in some situations, but not in others. I have an air conditioner in my room upstairs, and I plug it in, and it works just fine in the upstairs. But if I take it away from, if I put it in the basement or during the winter or something, it's not useful. It doesn't work then. I have a
But
car.
But that means that you are turning it on.
That's right, and viruses are on, and if viruses are no longer in a body, they can sometimes exist just as molecules on surfaces, and then when somebody comes by, they can infect them if they touch the surface. So I don't understand why, if if the virus is not infecting something, it's not dead. It's not really alive either.
That's why I'm asking that why such that virus, if they are lying as it is, they are just a protein. If they are lying, they are just a molecule. It's a protein. But if they come in contact, they come to living. So how come they are energized?
Well, that's a good question, and life is a notoriously difficult thing to define, and some scientists
and they become so notorious because COVID was also a virus. COVID is also a virus, and they are dead.
Right.
For a moment, they are dead. But when we get in contact with them, they are living. They are energized. They infect everyone.
Yes. Yeah. Sure. But whether they are dead or just inanimate, like a machine, is a different question. Those little machines in Star Trek that I showed it by the blood cells, you could see they were made of metal and stuff. They might be inanimate. If we put little nano robots in our bloodstream, those might be inanimate, unliving, and they could still kill us nonetheless. The viruses that enter our body, they take advantage of our systems, and they do us damage. But the point is here, I don't want to get bogged down in trying to define life, because again, other people have tried and have had trouble. what I want to show is purpose and design. And I think people can see even in viruses like that bacteriophage T4 that we saw, that those things are, that they have a purpose, and therefore they are designed. We can tell that they were designed. They have many different parts that have been arranged, whether you want to call them living or dead, you know, whatever you'd like, but they're clearly purposeful. Okay, I hope that helps a little.
Thank you, sir. Part 7, your question.
Yeah, thank you, Dr. Behe, for the amazing seminar. I've been like watching your videos for about probably 10 years now. I've shared those with a number of youngsters, and they've all like, find them very interesting, especially this the irreducible complexity in the comparison to the flagellum of the bacteria. My question is that I am a student of social design, and we work on, or we think of solving social problems through design thinking. So in my experience with people over like the past like 1 year that I've been through the course, what I feel is that this scientific understanding of whether life is a work of chemicals of matter, or is it something beyond of that, this plays a very important role in establishing the way people want to live their lives. Life becomes sacred, it becomes divine, and our life has a purpose when we see that it's not just matter. And when one sees as matter being the force behind life, then life becomes I would say we become insensitive, become dehumanized. So this is what I feel, and I want to know your opinion, whether like what do you think about this?
Well, yeah, I agree with you. I think that one big problem with our modern world is that people have become convinced that there is no purpose, that there is no design, that do what you want to do, nobody cares. You can live a good life, you can live a bad life, you can live a life just for yourself, do whatever you want, it doesn't matter anyway. And that is profoundly dispiriting for people, and they will despair. And why not? Because if it's true, then there is no hope. So I'm, you know, the work you're doing is sounds to be wonderful. It's a big problem, and the ironic thing is that modern science, the science itself, rather than a lot of scientists, modern science is showing us exactly the opposite, that we are planned, we are built down to a very fine detail, and the intelligent being who made us down to such detail, you can assume will care very deeply about our lives and about what we do, and whether we do good things, or if we just live for our own pleasures, or whatever. So yeah, all of these things are quite related. And I think the world got off on the wrong foot when it accepted Darwin's theory without really knowing how life worked. But that's where we find ourselves, and it's up to us and people who share our views to try to get the word out and try to counter this problem.
Thank you so much.
Mm-hmm.
Thank you, sir. We'll now request Vishal Rana to speak.
Thank you, Dr. Behe, for such a wonderful session. I'm really like inspired by your videos, your work. Especially recently, I saw your new video of magnetotite crystals in bacteria. That was really amazing. That was really amazing.
Yeah.
That such complexity is there in the cell. So I'm really motivated and inspired by your work and your theories. So I have a question that these things are very important and have a logic and evidence. And Darwin things are like most of the things, as you have explained, they are like stories, and Mostly like it seems to be a fairy tale. But why in the modern world only Darwin's theories are taught in schools? Why not these intelligent design theories that are very logical and plausible that should be taught? And why these people are actually basically biasing atheism? And if yes, you agree on this point, then what can we do to improve the situation?
Okay, that's an excellent question. Why, if Darwin's theory doesn't explain what modern science has discovered, are schools not teaching that or pointing that out? And when people do try to get that taught in schools, they are met with a lot of opposition. And that's a very, very complex topic, but let me say a couple of things. Number one, it has such fierce reactions from people because it touches on questions which are very that deal very closely with who we are and what we are. And a lot of people want life to be a certain way, and they will fight fiercely to make sure that society reflects that. So if there's a large, unfortunately, there's a fraction of scientists, certainly not all, not even a majority, but there's a fraction of influential scientists who don't want life to be designed, who don't want life to have a purpose, even if that would be beneficial. They just don't want that. And they want to be in charge. They want to tell you how life would unfold. And if the evidence points strongly to design, they can always just say, well, that's, giving up. Science in the future will explain this. Additionally, since design, even though design is an empirical conclusion based on the physical evidence, it does have philosophical and theological implications, pretty clear ones. And because of that, depending on which country you live in, what your government says, what your society says, that can affect whether or it can be taught to school children in government schools. Since many societies are composed of all sorts of different cultures, some cultures worry about other cultures getting an upper hand, and important matters are sometimes very closely regulated by the government. And even if the evidence points one way, some people might not want design to be taught in schools because they think some other group will use it to get a political edge or cultural edge or something like that. These are complex questions, and in some cases they might have a point, but I am no sociologist, and I'm no politician, and all I can say is that I'm confident that in the future this will become the dominant view, where if people read about it and promote it or tell other people about it. And the reason is that this is what the science is showing to be correct. This is what the evidence is showing to be correct. And although some people don't like it, you can only ignore the evidence for so long, and eventually the resistance will come down. How long that will take is a different question, but I am very confident that eventually this will prevail.
Yes, sir. Thank you very much for that amazing answer. The truth shall prevail. That is our hope, and that is the way we are. We are trying our best. Like you have been trying your best, and we are doing the same. So there are many more questions, sir. So I think we'll have to have another session with you if you can kindly allow.
That'd be wonderful. That'd be wonderful.
Yes, sir.
Okay.
Because a lot of people that I know and a lot of people that we told about, they wanted to attend the session, but some or the other reason they could not attend. So we have recorded the session and we have done it live on our YouTube channel. So we'll be sharing the recording. But we'll be more than happy if we can have you once again and answer these questions and explain this incomprehensible facts in simple language like you presented it today.
Good.
So,
And tell people who didn't get a chance to ask a question that they can just email me at Lehigh University. My email address is my initials MJB and then MJB1 at lehigh.edu, and I'll be happy to respond to your questions.
yes, I have sent the mail ID on the chat, Zoom chat, so they can copy and ask directly to you. At the same time,
Super.
we'll be conducting many more such sessions, and we'll be inviting Professor Behe once again, as Sir is again confirming himself, and many other such scientists. So, in order to fulfill this inquisitiveness that we have, and I would just like to express my heartfelt gratitude to you, sir, for taking out your time. It is actually 8 a.m. It was 8 a.m. in US where sir is staying. So
Yeah,
on a
it's
Sunday
early.
and a Sunday 8 a.m. is really difficult, but sir is very dedicated and committed to his work. And when I first proposed this, that it is a group of teenagers and young people who want to hear, so sir at once agreed that yes, I will be speaking to them. So that also really speaks about how much passionate sir is about his work and how he wants to share this knowledge with others. So
Yeah, sure. It's very important.
yes, very important.
Okay. Well, and let me just say thank you very much. I'm delighted to have been given this opportunity to let you know it's very important. It's so sad that many people think that science has shown the opposite of what it has shown. That it turns out that nobody should be afraid of knowing more and more about the world, because the world reflects its designer, and the more we know about it, the more we'll know about that.
Yes, sir. So this was just a small trailer, and we have sir's many lectures available on Discovery Sciences YouTube channel. We have this very special series, Secrets of the Cell. It has 6 episodes right now. The latest episode was released 18 minutes long. There's a wonderful, wonderful series which just talks about these detailed concepts with amazing clarity and wonderful cinematography as well. So you will enjoy watching this.
Good. Thank you.
And if you want to go into detail, there are 3 books: Darwin's Black Box, Darwin Devolves, and The Edge of Evolution. So once you go into that, this is just like an ocean, and you immerse yourself into it, and you will just and you will love this. So with this, I would like to end today's session. We'll continue with our next session next Sunday. Thank you once again.
Thanks. Thank you very much.
Hare Krishna.
Bye bye.
आप सबका भी बहुत बहुत धन्यवाद ज्वाइन करने के लिए. I have sent the feedback form. You can fill in the feedback form so that we can get to know for our improvement what all we can do and what all topics would you like to hear for such sessions. And you can also share what all things did you like and how we can improve. Any other questions that you have, here is my contact number. You can send it to me, and you can send it to Dr. Behe as well. We can be in touch. Thank you. Hare Krishna. I would like to thank on behalf of ISKCON Gurugram also. Our temple president just left for an important meeting. So I would like to thank our temple president also, as well as on behalf of ISKCON Gurugram, I would like to thank all of you who have joined for this session, who spared out their precious time on a Sunday evening. Hare Krishna.